workshop. I'm Liang from University of Pittsburgh. I'd like to acknowledge the development team members of the CyberWater project. They are listed here. In this slide, all the team members of the CyberWater project are listed. I'd like to acknowledge their contributions to the project. So, what is CyberWater? Well, CyberWater is an open and sustainable modeling framework software system. It enables an easy and incremental integration of diverse data sources and models. It also enables reproducible computing and the seamless and on-demand access to various high-performance computing resources. As the CyberWater development team members, we aim at offering not only the capability of seamlessly automated machine-to-machine access from external data sources to models, but also the capability of allowing users to easily add different models of your own into the CyberWater system. This has been achieved through the open data and the open modeling architecture design, which is based on the data agents, model agents, or generic model agent tools and workflow. We have all of this in one place. So the motivation of developing the CyberWater system is to try to address some of the challenges that we face today. For example, the challenge of access heterogeneous data products. Oftentimes, these data products require different access protocols and APIs, and they often come in diverse formats. Models are usually very complex to run these days, and they require significant amount of significant data pre-processing efforts. Coupling of different models is another challenge, and it is a time-consuming effort. Many models now require high-performance computing capabilities. Another challenge is the reproducibility. Oftentimes, the simulations of case studies are difficult to be reproduced, even for the same research teams. I need to say it will be even more challenging for other teams to reproduce the results. So with all of these challenges, considerable amount of time have been spent by researchers and educators on the long vital tasks, rather than having their time being focused on the core sciences. So with that, we developed the CyberWater system. Here is a view of the overall architecture of the CyberWater system. The core of the system is what is called MSM core. Can you guys see my mouse?
Yes.
Yes.
Okay, thanks. So this is the core of the system. And you can think about it's the brain of the system. And MSM stands for Metal Scientific Modeling. The various diverse data products are connected to the core through the data agents. The various different models are connected to the core through the model agents. CyberWater uses the workflow engine of VIC and its user interface. So here is a preliminary view of what the CyberWater user interface look like. The center part here is the workspace. These different boxes are the different modules. Each module accomplishes certain tasks. These modules have been developed by the development teams of the CyberWater. You can drag these modules from the left panel here into the workspace and have them connected to form your workflow. And the workflow can accomplish what you want to accomplish. Okay, so the main functionalities of CyberWater that have been developed so far include the following. First, the data agents. With the data agents, one can access various diverse data products provided by different data providers. The next is the model agents, with which various different models can be easily integrated into the CyberWater system. Another way of integrating your models into the system is to use generic model agent tools. The difference between these two approaches is that with model agents, one needs to write a little bit code to handling the user interface. With the generic model agent tools, however, one doesn't need to write a single code. Both approaches don't require the users to modify their source codes, nor to recompile their source codes. All you need to do is to use your executables. CyberWater now can handle executables from C language, Fortran, Python, and Java. We are working on handling the MATLAB. And the other functionalities that we have so far includes model couplings. CyberWater makes the model coupling an easy task. CyberWater also has integrated with GraphGIS. What it means is that all the commands that are available in the GraphGIS can be used in CyberWater. CyberWater offers the on-demand access capability to HPC. CyberWater also offers the capability of fuse different data products or model results by using multiscale Kalman Smoother algorithm. CyberWater also offers a graphical workflow environment. It has it offers visualization and animation capabilities for people to display the different model results and the data products. CyberWater also has the province capability through the visuals. Okay, here are some examples where the diverse data products are accessed through CyberWater Data Agents. Up till now, we have developed more than 10 data agents, which allows us to be able to access in real time automatically different data products from different data providers. For example, we have a radar data agent, which allows us to automatically in real time access the radar precipitation data provided by National Weather Service, which is show up here. We can access data from North American mesoscale forecasting system provided by NOAA. We can also access data provided by a global forecaster system by using our GFS data agent, which is illustrated here. We can access soil moisture data provided by NASA from SMAP using our SMAP data agent. We can access GPP and NPP data from MODIS satellite. We can access precipitation data provided by NASA GPM satellite mission. We can access NLDAS and NCALDAS data provided by NASA from the NAT data assimilation system. In addition to the access of all those very diverse data products, we can also access data from USGS stations. By using our USGS data agent, we can access more than 13,000 USGS stations. Here is a map which shows where these USGS stations are located. We can also access geoscience data through the Unidata platform by using our Unidata data agent. We can access sensor data. For example, the the sensor data from the Iowa flood information system by using our IFIS data agent. Here is an example of that. In terms of the model agents, we have developed some model agents for the CyberWater system to make it easy for users to integrate these models into the CyberWater system. For example, we have developed model agents for the VIC model using both approaches. One is to use a model agent approach to integrate the VIC model into the CyberWater system, and also to use the generic model agent tools to integrate the VIC model into the CyberWater system. In terms of the VIC, we have in both VIC version 4 and VIC version 5 being integrated into the CyberWater system using both approaches. We have also integrated the routing model into the CyberWater system using both model integration approaches, that is model agent approach and generic model agent tool approach. We have, by the way, for those of you who are not familiar with VIC model, what a VIC model is, it is a net surface model. We also have a high resolution hydrological model, which is called the DHS-VM model, integrated into the CyberWater system using both approaches. We have a CASA model, which CASA CMP model, which is a biological model integrated into the system using the generic model agent tool approach. And the CASA stands for Carnegie Ames Stanford approach model, which deals with carbon, nitrogen, and phosphorus cyclings. We are planning to integrate 3 more models into the system for easier use by the communities. One is the Iowa flood information system model, which is called the IFIS model. The second is the WASI model, which is an ecological model developed by USDA Forest Service. The third model is an environmental model, which is called FreeQC, developed by USGS. So here is an example of the workflow showing you how easily it is to have a model integrated into the CyberWater system using the model agent approach. In this example, we have the VIC model integrated into the CyberWater system using the VIC model agent. Here is the VIC model agent. The forcing data required by running the VIC model are brought into the CyberWater system by using our data agent. So in this case, the NCA LDAS data agent is used to bring in the forcing data into the system. To run the model, you also need to specify the time range, which is a study period of your model simulation. And you need to specify the space range, which is the study area of your model simulation. With that, you collect these modules to form your workflow and execute your workflow in CyberWater. By executing it, CyberWater runs the VIC model and generates results. And you can visualize your results generated by the model. For example, in this case, to visualize your and output your model results for visualization. In this case, we output the surface runoff and the subsurface runoff for visualization using our visualization tools. You can also compare your model results with other data products, where you can bring in your data products using our data agents. In this case, we compare the surface runoff with the NCA LDAS surface runoff and display it by using our visualization tool, which is show up here. So the green is the VIC surface runoff, and the blue is the NCA LDAS surface runoff. The results of the VIC model is obtained without calibrating any model parameters for this Clarkson watershed. And this watershed is more than 2,000 square kilometers in size. Okay, this is another example in CyberWater where I want to show you how easily you can use CyberWater system to couple different models. So first of all, you need to integrate your models that you want to couple into the system and then couple them together to get the results that you want. In this example, in this workflow showing up here, we have the VIC model coupled with the routing model and using the model agent approach. So here is your VIC model integrated using VIC model agent. And here is your routing model integrated into the CyberWater using the routing model agent. And then you couple them together to form your workflow. For the routing model, it requires information such as the DM data and information of the stream flow network and the stream and the flow path network and so on. So in order to get such information, we invoke the GIS engine that we have in the CyberWater. Remember that the CyberWater system is integrated with GraphGIS. So we use GraphGIS to obtain all the information required by the routing model automatically and have such information automatically flowed into the routing model for execution. So here is this workflow, and by executing this workflow, you will obtain the model simulated stream flow from the routing model. And with that model simulated stream flow, you can compare it with the observed stream flow, which is brought in, and that observation data is brought into the system by using our USGS data agent. And so then you compare the USGS observations with the model simulations using our visualization tool to and display that for comparisons. And here is the result. The green shows the VIC model coupled with the routing model results, and the blue shows the USGS observations. And again, this result is obtained without conducting any model calibrations. Okay, so in the previous example, what I showed you is how to integrate a model into the CyberWater system using the model agent approach, and how to have the different models, the VIC model and the routing model coupled with each other. In this example, what I want to show you is how to integrate a model into the CyberWater system using the generic model agent tool approach, the second approach, and then have them coupled together. So here, if we look at the blue, the modules inside the blue box, these are the modules provided by the generic model agent tools. So basically, you use these modules and connect them together, and these modules work together to provide functionalities that are equivalent to the VIC model agent. In other words, you use these modules provided by this model agent tools to construct your own model agent. And in this case, your constructed model agent is shown by the modules inside the blue box. By the same token, you use this generic model agent tools and to construct your routing model agent. And again, using these modules here, you connect them, specify them, and to form the routing model agent. And these modules together, again, provide equivalent functionalities as our routing model agent shown in the previous example. And then you couple them together like this, and then you execute your workflow. And in this example, again, when you execute your workflow, you will get the simulated stream flow from your model. And then you can, again, compare it with the observations from the USGS and by using our USGS data agent. And so you use our display visualization tools to display them. And in this workflow, we apply it to a different watershed from the previous example. And in this case, it is a West Branch Susquehanna River Basin, which is rather large. And here, and this river basin is more than 17,000 square kilometers. This example shows you, give you a sense that CyberWater is not a baby toy. It can be scaled up to handle large simulations over large areas. And here is the result. of executing the workflow I just showed you. And the blue is a model simulated results from the VIC coupled with the routing using the generic model agent tools approach. And the green is the USGS result, observations. Okay, in this example, what I'm going to show you is that we also have this DHSV model, the high resolution hydroelectric model integrated into the CyberWater using the model agent. And here is this model agent. And the forcing data required by DHSV model is different from what the forcing data required by the VIC model. And so in this case, we use a different data agent to bring in the forcing data required by the DHSV model. And in this case, we use NLDAS data agent. And again, you can compare the results with the USGS observed data and show the results here. Okay, so in the previous examples, I showed you how to have models integrated into the CyberWater system and have them coupled, either by using the model agent approach or the generic model agent tool approach. And in this example, what I want to show you is that you can use both approach in combination to integrate your model and have them coupled with each other. And in this case, this example shows that we have the VIC model coupled with a CASA CMP model. And the VIC model is using the model agent approach, while the CASA model is using the generic model agent tool approach. So in this case, you have to construct your CASA model agent, and your constructed model CASA model agent is shown in this red box. What I want to also bring your attention to in this example is that you notice we have a module here, which is a component of the constructed CASA model agent. It is called run module agent. By using this run module agent, you actually execute your model, which is CASA model here, locally on your local machine instead of running and execute the CASA model remotely. Okay, so by building this workflow, then you can execute it, and then you can generate results and display it. And in this case, we generated the simulated carbon on leaves, and the results is show up here. In this example, what I want to show you is that CyberWater makes it a very easy job to either run your model locally or to execute it remotely on the HPC, which is a high-performance computing platform. So I will use the VIC model as an example again here. So in order to do that, you basically construct your VIC model agent by using the generic model agent tools. You have to use your the generic model agent tools in order to do this. So you construct your VIC model agent using these modules. And instead of using the run module agent, as I showed you earlier, you use the HPC module here and to execute the VIC model remotely on the HPC. So if you replace this guy by the run module agent here to refresh your mind, then you would execute the VIC model locally. But if you replace that run module agent when you construct your VIC model agent here by this HPC module, you will be able to run your VIC model remotely on the HPC platform. So CyberWater makes this to be an easy job. Okay, so in this example, what I want to show you is another capability that CyberWater has, which is to be able to fuse different data products using our data diffusion, using our data fusion algorithm based on the multiscale Kalman Smoother method. Here is a schematic representation of the concept of the MKS. For those of you who are interested in knowing more about this algorithm, you are welcome to read these papers. So what I want to show you in this example is to fuse 3 different precipitation data products over this 1 degree by 1 degree region. And this region covers part of the southwest Susquehanna River Basin. So here are the 3 different precipitation data products. The first one is the radar precipitation data from National Weather Service. We have this radar data brought into the CyberWater system by using our radar data agent, which is this one. This radar data has a 4-kilometer resolution. The second precipitation data product that we brought into the system is the GPM satellite precipitation data from NASA by using our GPM data agent. This data has a spatial resolution of 0.1 degree. The third product is the precipitation from the NCA LDAS, and we brought that in by using our NCA LDAS data agent. And this precipitation data has 1/8 degree resolution. Okay, by bringing all 3 different data products into the CyberWater system using our 3 different data agents, we can have this done in real time, and this is done in real time automatically. And so by having this data brought into the CyberWater system, then you can use our MKS data fusion module to fuse this data. And then you can use our visualization tools to display the results. Here are the results. So the first row here shows the radar precipitation data product that are brought in into our CyberWater system. And it is displayed at 1/32 degree resolution. The second row shows the precipitation data product from satellite, the GPM satellite. It is also displayed at a 1/8 degree resolution. The third row shows the precipitation data product from NCA LDAS. It is also displayed at 1/8 degree resolution. And the last row shown up here is the fused precipitation data based on the 3 different data products here. And it is displayed at 1/16 degree resolution. Each column here shows a 1-day precipitation, and we have 10 days here shown up. So by looking at these results, you can see that sometimes the magnitude of the precipitation and their spatial patterns are similar to each other among the 3 data products. But sometimes their magnitudes and the spatial patterns are quite different from each other among the 3 precipitation data products. And so with the CyberWater system, you can easily bring this data into the system and display them and analyze them. Not only that, but also you can fuse them using our MKS algorithm by taking advantage of the strengths of each data product. Down below here, what I'm showing you is the time series of the time series of each of the 3 different data products, plus the fused MKS time series of precipitation. Each point here shows the mean average of this area. Okay, so with all that examples, in summary, CyberWater has some unique characteristics, and they include first, its novel architecture enables a dramatic reduction in model integration complexity. CyberWater has a linear model integration complexity, as opposed to a quadratic model integration complexity compared to those pairwise model integration system. As we know that linear model complexity is the lowest complexity for a model integration system. And CyberWater's effective model agent tools enables an easy model integration and model coupling with little to no coding. CyberWater's capability, CyberWater has the capability of incorporating diverse data sources and have this data automatically flowed to the model in real or near real time. Its new high-performance computing facility enables an easy access to HPC on demand. Also, CyberWater has the capability of supporting workflow and reproducible computing through adoption of visuals. The significance of CyberWater system includes the following. First, it offers an open and sustainable platform that can maximize the level of harmonization among diverse data sets for various model intercomparison, evaluation, and model integration activities. CyberWater facilitates multi-model assessment using multiple data sets. It also facilitates team collaborations. We plan to have CyberWater system to be released to the community next year. Okay, so what would we like to achieve from this CyberWater user workshop? Well, we like to first brief the development of the CyberWater system to you, the audience, and that is what I just did. Second, we like to illustrate some of the features of the CyberWater system through 4 demos, which will be presented to you by 2 PhD students, Daniel Noonan from Pitt and Zhen Chen from IUPUI. We like to seek comments and feedback on the features that are included in the CyberWater from you, so that it will help us to increase its utility to education and research. At the end of the workshop, like Rick mentioned earlier, that we will conduct a survey. We really appreciate your valuable feedbacks on our system and your participation on the survey. With that, I'd like to conclude and thank you all very much. Are there any questions?